Hello again. This is video lecture 36.1. We're discussing the first section of chapter 36, and chapter 36 is all about the phenomenon known as diffraction, which is a wave-like phenomenon like interference, and it is in fact related to interference. And we're going to start with a specific application where diffraction occurs and kind of develop our understanding of diffraction within this particular application. And it's called single slit diffraction. And I want to talk about exactly what we mean. For the last experiment we're doing in lab, you may have, if you have been doing part B of the experiment, you have come across this single slit diffraction. The way you do the experiment is you have some kind of a screen and you cut into that screen a opening that tends to be long and narrow. And I've represented that very schematically here on the left. The screen is the rectangle that's kind of hatched across with lines. That screen would be otherwise opaque to visible light. Visible light can't just be transmitted through it. But we have cut a long, thin opening called a slit. And the key dimension here is the narrow one, not the long one, the narrow one, the width of the slit, which the book uses the symbol little a to represent. And we send in what's called coherent light. In modern day applications, that would be done by shining laser light on the screen with the slit. Okay? So let's just say the slit then is what you see if you're the laser light coming towards it. You are coming right towards that screen with the slit, and you're a light wave. What happens to you when you go through that slit? Well, you have a combination of two main things, and those two things together are what we call diffraction. And one of the things that happens is basically what we'll call flaring of the light as it passes through the slit. So when the light goes through this narrow slit, on the other side, the light wave fronts coming in that were planar, flat, now bow outward. They get some curvature. Okay? And a very simple representation of that I'll draw over here with not a front view, but a side view, with the long part of the slit coming out of the screen and the narrow part of the slit visible here, A. And we are sending in planar wave fronts. So those are represented in a side view by a set of parallel lines. And the spacing between those adjacent wavefronts is the wavelength, lambda, of the light. Now, when the wavefronts impinge on the screen, and the part of the wavefronts that can get through the slit, they do so, you can think of the slit opening as being consisting of a whole bunch of little points of sources of spherical wavelets, Huygens principle. And so the net effect of those little wavelets propagating outward is that the wavefront now curves or bows on this side. And that's the flaring I'm talking about. Okay? That's the flaring phenomenon. That's part of diffraction. The other part of diffraction is that over the front of the slit, if you imagine having a whole bunch of those little point sources of spherical wavelets, each producing their own wavelet going outward, then over here on the right, if you've got some viewing screen over here, you can get interference of those wavelets. And it's the combination of the flaring, giving you the rounded wavefronts, and the interference that together is diffraction and produces what we would observe on the viewing screen, which would be what we call a diffraction pattern. All right, now, the photograph in the middle here is an actual photograph of an actual diffraction pattern. And it was made by shining coherent light on a vertical slit, much like the one I've drawn on the left. And then the light goes through that slit, the vertical slit, and the flaring is now this way. So that's a bit different, let me be clear, to the situation I drew here, okay? In my side view, I drew the slit as being horizontal, and then the flaring was up and down. But if the slit is vertical, then the flaring is left and right. And then on the viewing screen across the way, the diffraction pattern will be left and right. And that's what this photograph is. Okay? So don't be confused by the length of the pattern that you see up and down that way. That's not the important thing. The important thing is what you see looking left and right. You see a very bright band here in the middle called the central maximum. And then if you look very carefully at this deliberately overexposed photograph, you'll see on either side, I'll draw it in kind of a light green, is a dark band there and there. And that's called the first minimum. And it's along those lines where you're getting fully destructive interference. Then, if you look very carefully, you'll see another bright fringe, although certainly not as bright as the central maximum. But it's there if you look carefully. There's one there, and there's one there. And then a little farther out, again, look very carefully, there's another dark fringe. There, and there. And then, again, look very carefully, there's another bright fringe. There, and there. And so it alternates. Dark fringe, bright fringe, dark fringe, bright fringe, going, in this case, left and right. And this is what you saw if you've done part B in the last experiment. You saw, when you specifically shine the laser light on the one slit, the single slit configuration, then you saw horizontally, left and right, on the wall across the room, alternating bright, dark, bright, dark, bright, dark. You were seeing a single slit diffraction pattern with the central maximum in the middle, which is by far the most intense, and then side minima, the first side minima, and then another, and then side maxima, and then side minima, and side maxima, and so forth. All right, now, we want to be able to understand this diffraction pattern quantitatively with some numbers. And it turns out one of the things that it's relatively easy to locate on the viewing screen is where those dark fringes are. And I'm going to show you a little technique for deriving the formula that will allow us to locate the dark fringes. Okay? All right. So, what we have here is a picture, a very schematic picture, of the single slit geometry. Let me zoom in a bit so you can see it a little better on the left here. Okay? And what we want to do with this picture is locate the intensity minima in a single slit diffraction pattern of width A. And we're going to find the first minimum. Okay? The first. All right, now let me show you the geometry. We've got to be clear about it. Okay, screen B going up and down, and it's got the slit cut in it. Now the long part of the slit is coming out of the screen towards you, and then this way is the narrow part, and that is a total width there from top to bottom of the slit, little a. They have then taken the midpoint of that slit and drawn a dashed line, they call it the central axis, over to screen C, distance big D, and we're going to view the diffraction pattern on that screen C. So it's called the viewing screen. And that point on the central axis, on the viewing screen, directly across from the center of the slit, they label P0. All right, and then they've picked another point, P1, and they want that point specifically to be the first point on the viewing screen where fully destructive interference is observed, i.e. a dark fringe. Okay? All right, now what they've done is with that central axis dotted line going across, they have, quite nicely, divided up the slit into two equal portions, a top portion and a bottom portion, each of width a over 2. And then they have intentionally picked a ray from a wavelet starting at the very top of the slit and going over to point P1. That's the ray they labeled R1. And then a ray at the very, think of that ray R1 as at the top of the top half slit. And then another ray at the top of the bottom half slit, right there. Also going to point P1. Okay? All right. Now I want those two rays, when they meet at point P1, to destructively interfere. Then their intensity contribution is 0, nothing. And then you can imagine a little Huygens wavelet source just below that top one in the upper half slit, and just below that top one in the lower half slit. And you can take those rays to P1, there and there. And you want those two to destructively interfere with each other. And then take another Huygens wavelet just below the top one there and that one. Draw the rays to P1, and you want those to destructively interfere. And by pairing up points in each half slit that are each a distance a over 2 apart, and requiring that they destructively interfere at point P1, you know you'll get dark. You'll know you'll be at a point where there's darkness. Fully destructive interference. Okay? And that's the kind of trick here. All right, now, the next picture over to the side here is a blown up view of the upper half slit, the upper half, a over 2. There's that ray R1 going off to point P1, and here's the ray R2 going off to point P1, including this part of it, right there. Now, here's something that this picture is showing that the picture on the left does not show. The picture on the right is assuming that the distance big D is very large compared to A, which the drawing there definitely does not imply. In that sense, the drawing on the left is misleading, because we're going to assume that the distance big D is large compared to the A. If you've done part B in the experiment in lab, you know that's true, because the distance big D is the distance from the glass plate all the way across the lab room to the wall, whereas A is the width of a slit, which is tiny. Okay, so the picture on the left is a bit misleading. In fact, the distance big D is so large that the two rays that I'm talking about here, right there, that are going to be combined at point P, and that we want to destructively interfere with each other at point P, are in essence parallel to each other. Now, they're not exactly parallel, but the distance D is so large that they are pretty close to being parallel. Okay? That's going to be important, as you will see. All right, now, because I want those two waves to destructively interfere, then I know that the path length difference, delta L, between them must be, in this case, half a wavelength. That will put them crest to trough, and they will fully destructively interfere when combined. But because I'm using this geometry here where the rays R1 and R2 are parallel, I have a nice little right triangle over here, right there, with a right angle and a hypotenuse, etc. And if we take the angle theta, this is important, to be the angle between the dashed horizontal line going across to the middle, called the central axis, and the line going up to point P1, up here, that's the angle theta, then that angle theta is also this angle here. And so the length that I have drawn in green is the path length difference. It's the extra distance that ray 2 travels compared to ray 1. So just from geometry, I know that delta L is the length of that green side of that right triangle, which is the hypotenuse times sine theta. And the hypotenuse is A over 2. So A over 2 sine theta follows from geometry. Now just combine these two. These are both expressions for delta L that have to be equal. So you get A over 2 sine theta must equal L over 2. Excuse me, lambda over 2. I beg your pardon. Those cancel. And so A sine theta must equal lambda. And that turns out to be the condition for locating the first side minimum on either side of P0. Okay? So I'll write that formula, bring that down a little bit, right below here. A sine theta must equal m times lambda, where m is an integer equal to 1. And so we have our first dark fringe. And note, by the way, the whole pattern is symmetric about the central axis. So if the angle theta here locates the first dark fringe at point P1, then equidistant below P0, I'll try to get it equidistant, there'll be another point P1 down here, which will also be a dark fringe. And we've located the first dark fringe. Okay? But that's not the only dark fringe. If you've seen the diffraction pattern on the wall, you know there's more than one dark fringe. So let's next find the second dark fringe, the second minimum. Now the trick you do is you imagine breaking up the slit A in the screen B into 4 equal parts, each of width A over 4. And you take the top Huygens source, point source, in each slit. Okay? The top source in the topmost slit, then the top source in the next slit down, then the top source in the next slit down, and then the top source in the bottom slit. And you draw a ray going to the point P2 now, locating the second dark fringe. Okay? The point P1 located the first dark fringe. I'm now locating the second one, P2. And so you take the rays R1 and R2 and R3 and R4, all converging at point P2. And if you want it to be a dark fringe, then here's what has to happen. You get cancellation by grouping the rays in pairs. The top 2 rays, R1 and R2, you require that those two, the waves from corresponding to those 2 rays, must fully, destructively interfere. And then you also require the waves from the bottom 2 rays, R3 and R4, to fully, destructively interfere. I'll abbreviate. So then again, I will have darkness at point P2. And then you can look at other sources. You could look at that one and require that those 2 together cancel. and then that one, and that one. It's just below there. And you require that those two pair cancel. And you can do that all up and down the slit. And everything's canceling by pairs, so you have a dark spot. Okay? All right. So let's look at these bottom two right here that must fully destructively interfere. Then I know that the path length difference must be a half a wavelength. That's the requirement for destructive interference. But then I also can use geometry to get the path length difference. Now let's consider arrays R3 and R4. There's R3, and there's R4, both going to point P2, but R4 also has that extra bit right there. And that's the extra distance that R4 travels compared to R3. And so that's delta L, the path length difference between R3 and R4. And again, I have a nice little right triangle right here with a right angle and a hypotenuse, A over 4. And if the angle theta now between the central axis, this way, and the line going out to point P2 is theta there, then this angle up here is also theta. And geometry tells me that delta L is then hypotenuse, A over 4, sine theta. Now those are both expressions for delta L, so they must be equal. A over 4 sine theta must equal lambda over 2. And I can get some cancellation. I'm left with a 2 there, and I multiply both sides by 2, and I get A sine theta must equal 2 lambda. And that leads me to the condition to find the second dark fringe, which I've written here. A sine theta must equal m lambda, where m equals 2. And that will give us the second dark fringe. All right? Now, you could continue this process, always dividing the slit with A into an even number of parts and requiring that pairs of waves fully destructively interfere, and then you'll just have a bunch of destructive interferences and you'll have darkness. And so what you can really do then is just generalize to locating the mth, if you like, dark fringe. A sine theta must equal m lambda, where m can be 1, 2, 3, ... All right, so the first dark fringe on either side of the central maximum is m equals 1. The second dark fringe, the next pair farther out, is m equals 2. The third dark fringe is m equals 3, and so forth. Note, this formula does not include m equals 0, because there is no dark fringe that satisfies that formula. That, in essence, is talking about the central point, the point P0, which is a bright fringe. We know that. So be careful with this formula. It's A sine theta equals m lambda. M is 1, 2, 3, ... And it locates the dark fringes. Do be careful. This formula locates the dark fringes. I say again, it locates the dark fringes, not the bright ones. Now, I know some of you are wondering, well, wait a minute. If you can use this kind of thinking to locate the dark fringes, why can't you do something similar to locate the bright fringes? Why don't you take these pairs of waves and require that they fully constructively interfere and then find the bright fringes? That's a good question, and that one's subtle. It turns out that doesn't work for finding the bright fringes. I'll explain a little bit in a very simple way. Okay? First, here's why this method does find the dark fringes. Okay? I'm going to think of it as vector addition, because it's kind of like a vector addition. Let's say I've got a bunch of vectors that in pairs cancel each other, like there and there, right? Equal magnitudes, opposite directions. Now let me draw another pair, there and there, and those two cancel. And another pair, there and there, and those two cancel. We'll just do 3 pairs. And I've drawn them all, at least I tried to, so that they are all equally spread around and with equal angles between them that way with the red arcs. And I'm just adding up a bunch of zeros, right? Because the net vector, whatever it is I'm adding here, of those two is 0. The net of those two is 0. The net of those two is 0. Add up a bunch of zeros, you get 0. So that's what we're doing to find the dark fringes. We're adding up, we're considering a bunch of destructive interferences. A bunch of destructive interferences is dark. Okay? All right, now, why doesn't this work to find bright fringes? Constructive interference. Okay, now what I'm going to do is I'm going to pair up these vectors in a way so that in pairs they combine. They don't cancel, they add. So for example, the two here are drawn like that. Well, those don't cancel each other, right? They do not cancel. Those two combine, big. But now, here's the next two. Okay, they don't cancel either, do they? They add, big effect. And then the last two. Those two don't cancel, they add, big effect. But these angles, here, here, and here, are equal. And if you add the net vector here, which would be something roughly like that, and the net vector here, which would be like that, and the net vector here, you get 0. Okay? So the bottom line is, just because you're adding up a bunch of paired constructive interferences doesn't mean the net effect is constructive interference. But for destructive interference, you are adding up a bunch of zeros. You got to get 0. So the clever little trick of pairing the rays only works for finding the dark fringes. That's my point. Only works for finding the dark fringes. So I say again, this formula finds the dark fringes, not the bright ones. Now, it is a general rule of thumb that a bright fringe is approximately midway between two neighboring dark fringes. So if you can find the angle for two neighboring dark fringes, then the angle for the bright fringe in between is roughly midway between those two angles. And that's a rule of thumb, and that can be helpful. But there is no formal equation for calculating the location of the bright fringes. We have to be satisfied with the formula for locating the dark fringes. And we will be talking about this in our class next. So I will just leave you with another class engagement question on Blackboard. And it goes like this. We're going to produce a diffraction pattern on a viewing screen by illuminating a long, narrow slit by blue light. That means light of a particular wavelength. All right. But now what we're going to do, so that's what we start with. We're going to switch from blue light to yellow light of a different particular wavelength. So my first question is, what's happened to the wavelength of the light when you switch from blue to yellow? Does the wavelength get bigger or does the wavelength get smaller? That's the first question. Next, because of this wavelength change, right, you illuminated the slit with blue light, and then on a viewing screen across the way, you saw a diffraction pattern. Right? Now you change the experiment and you illuminate the same slit with yellow light. Because of this wavelength change, what happens to the maxima and the minima of the diffraction pattern, specifically their spacing? Do the maxima and minima of the diffraction pattern shift further away from the central point, or do they shift closer to the central point? Because you changed this wavelength from blue light to yellow light. Lastly, keep the yellow light there, illuminating the slit, but decrease the width, A, make it smaller. There are such things as adjustable slits. Okay? Make the slit width A even smaller. Now what happens to the maxima and the minima of the diffraction pattern on the viewing screen? Do they shift away from the center or towards? Those are the questions that you answer on Blackboard. And as I said, we will be discussing this single slit diffraction in class, and you will be using it also as you finish up the last experiment. And that's all for this video.